Okay, calculus students, still in chapter 6, still applying the definite integral. And let me hit save. Bye-bye. Moving on to 6.5. The whole section is called work and fluid forces. Work, I am sure you've done a little bit of this with a constant force in physics. You didn't do variable force because that would require the integral. Work would require that. Also, probably in your physics class, when you dealt with work, you just used a simple formula, the constant force times the distance that you moved the object, most likely left or right, because then you didn't have to worry about gravity affecting it. But it might be possible that you did talk about lifting something up, or well, why would you lift something down? You could, well, you could take a spring that's attached to the ceiling, and you could stretch it down. That would be another force, but that's another force being used to do that. And you can do work on a spring. So maybe you worked on that. But definitely you did a constant force. And if you're in the English system, your unit for work was in foot-pounds. If you were in the metric system, you had to do Newton meters, which is actually 1 Newton meter is 1 joule. Okay, maybe that rings a bell with you. Fluid forces is like forces underwater, and you're in a submarine and you got these windows, and as the water hits that window right here, it applies a force. The deeper you go in that submarine, more force is hitting that window from the side because you got more pressure from the water. So you probably didn't do any of those in your Physics 1 class. Today, I said part 1 because I'm not going to merge these two together. I just want to do the work, okay? As a matter of fact, I didn't even get through all of this that I wanted to yesterday. So I will stop where everybody else stopped. That way you don't have to get ahead. Well, yeah. Work done by a constant force, very similar to what you would have done in your physics class. Oh. Object is moved along the distance along a straight line as a result of being acted on by a force of constant magnitude F in the direction of motion. We define the work to be done by the force with this formula. There it is, force times distance. Suppose you pick up the side of a 2,000-pound car. So you've got this car, and it's parked, and you only want to lift up half the car. Why would you lift up the whole car? You're going to fix this tire, so it isn't unreal to think that you're going to be using a jack, and the jack has this mechanism that attaches under the car, and then you have a handle that you go up and down with it, and it picks up that car. So every time you push that jack down, no matter how much force you're applying to it, the jack is going to go click, click, click. Even if you push it harder, it still does one click. That one click stands for how high that car got lifted up at that time. So let me make that tire smaller. Yeah, like I really am accurate. So you're lifting up just half that car here. And so in this problem, that means you're only lifting 1,000 pounds then, because it was a 2,000-pound car. You're lifting up one side. So you have to imagine I'm looking at the side view or the back end of the car. And let me put my little light so you can see that there are, well, better put red because you're used to your lights back here. So, and you're sitting in here. You're sitting here driving your car. And there's a steering wheel in front of you. So anyway, you jack up to 1,000 pounds of the 2,000, and every time you hit click, it moves up a little bit. Click, click, click. Maybe you have to press it 5 times to get 1.25 feet to change the tire. The jack always, the jack is always applying a constant force. No matter how strong you are, you might only need 30 pounds of pressure, of force to make that jack move. But even if you applied 100 pounds, it's still going to only move up the same distance each time. The only difference is you could probably do it faster if you're stronger. Okay? That's the advantage, the mechanical advantage of a jack. It takes a little person, can jack up 1,000 pounds. Okay? We want to calculate the work done on this. Well, the work done by the jack. It's constant force, so work equals constant force times the distance. Your constant force of the jack was constant force is usually like a weight. So it's 1,000 pounds, and the distance is 1.25 feet. Do your calculations. That gives you, move the decimal 3 times, 1,250 foot-pounds. Maybe you never worked up foot-pounds because AP physics tends to stick with metric system. But it is possible to do your work in the English system. We'll bounce back and forth. There it is, 1,250 foot-pounds. Okay. Now, he added more to this problem because we said the work performed the jack is, there's that answer. He wants it in the metric system. So to do the same problem in the metric system, you need to be talking about meters and you need to be talking about newtons. That's how you get a Newton meter. So I did some calculations in advance, and I realized that 1.25 feet is actually 0.381 meters, rounded. And 1 pound of weight that we use in the English system is the same as 4.448 newtons. Okay. So work will still be force times distance. And let me try to do it differently than I did in the other class. Let me say work. Oh, I don't want to do that. I want black, and I want that. Work was my 1,000 pounds times 1.25 feet. That's foot-pounds. I don't want it in foot-pounds. I want it in the metric system. So I'm going to do my dimensional analysis, and I'm going to multiply by a fraction to get rid of pounds. So if I know that 1 pound is 4.448 newtons, and and then 1.25 feet was the same as that decimal was 0.381 meters. You realize that the pound unit cancels out the pound unit in the numerator. The feet unit cancels out the feet unit here. As a matter of fact, the 1.25 cancels out that 1.25. So I'm left with 1,000 times 4. What did I say it was? 448 newtons times 0.381 meters. So that turns into 4448.381. That's still newtons, and that should be meters. And let's try that out in the calculator. And wait for it. I'm going to put the calculator picture. There it is. That is, I'll round that to, what do I have here? 1695. 1695 Newton meters, which means, there's my Newton meters, 1695 joules. I did this one a little different than I did with the other class. The other classes I went and showed them the same values. Then I did it right from my foot pounds, and I multiplied by a 1.3556. That was because I already multiplied those two together, and we get the same answer. 1695 joules. And I played around with it a little more. I don't know why. And 1695 joules. All right, let's do work done by a variable force that does require calculus. Now, since work is force times distance, I could see you adding a force to move this object from part A to B. And you may not have gone very far. You may have only gone whatever 1 unit is, right? And the force you applied, I'll call it F1. Then you decide to move the object more, and you apply a different force, I'll call it force 2, and maybe the distance was even longer. Maybe it was 2 units. It doesn't really matter. The point is, if you choose even a lesser force, I'm going to say F1 is greater than, I'm going to say it's less than F2, and I'm going to say F2 is less than force 3. So you go another distance, and it could be 5 units, and that's a lesser force than F2 was. Really doesn't matter to go to point C. So there's B and there's C. The total force, the summation of F, and I just put he used a constant, a CI, so it doesn't really matter. It's just some constant not constant, but different forces, depending on if I or K, which one was he doing? He's doing K goes to 1 to N. So how many pieces do I have times those different distances? Okay, different distances. Every one of these distances were different. Every one of these forces could be different. You total that up, the summation, there you go. But how does calculus apply? Calculus says that as you go from A to C, that the force could be changing all the time. It doesn't have to change from A to B. The force could be changing from A to a little bit more, to a little bit more, a different force, a different force. Maybe it's increasing forces as you increment up. Maybe it goes down, maybe it goes up, maybe it goes down. Who knows? It doesn't really matter. And we're not stopping at B. We just keep cutting this up. And if I zoom in on this, you can see that in between these two little small pieces, there are more smaller pieces that the force could be changing. See, I could go, and then if I really was a rebel, and I have been called that, I could even go in farther and say, well, I could slice it even closer. See? So my question to you is, since you're now calculus experts, how many different forces could there possibly be? And how many different distances could there possibly be? I mean, a hair width is a hair width, but some hair is thicker than other hair. So you could have that be variable too. But each of those hairline distances, and look at when I zoom in, there's still room in there to get more in here. There's still room. And if I zoom in a little more, look at that, I can even get more hair in here. The question is, how many different force distances could there possibly be? And I hope you say infinity. So it's the limit as n goes to infinity of the sum when k starts at 1 and going to n. N is going to approach infinity. Infinity number of steps. Look, you can't even see those hairline fractures anymore. I had to zoom in a super lot just to get, look at that, super lot. Look, now I can zoom in on the blue. See? Hope that was enjoyable. And you're still doing force times distance. You're still doing force times distance. Delta x is the distance. And the notation, different k's. So you got different forces. This was k, different k's here too. So it's all good. And in calculus, when I have all of these different to infinity, it's the integral from a, in this case, I'll start to c, of my force equation. Force is a function of x, and then you got your distances also could be a function of x. F of x dx. Okay, so let's do our first one here. Lift an elevator. An electric elevator with a motor at the top. I didn't understand if they meant top of the elevator or top of the elevator shaft. I wasn't really sure. I drew the picture both ways yesterday. When I read it closer, I think he has the motors at the top, perhaps. It has a multi-strand cable weighing 4.5. When he says that, it means it's a heavy cable, okay? It's a heavy cable because he's got a strand of wiring cable. Then there's another piece being twisted in there. And then there's another one being woven around in there. And it's really, really strong. And so the car is on the first floor. So when I think of first floor, I think of the car being down here at the bottom, right? He says that the 180 feet of cable are out. So that's 180 feet of cable. And effectively, let's see, uh, 0 feet are out when the car is at the top. Okay, that sort of tells me that there's this motor up here then. There's a motor up here that's cranking this cable up to lift the elevator, okay? So when you lift the elevator all the way to where the motor is, here's the top of the elevator now, there's no cable out, okay? And how much work is done on the motor to just lift the cable? We're not talking about lifting the elevator. There's actually work to lift that cable when it takes the car from the first floor to the top. So to move from this picture to this picture is what we're talking about. How much work did I do to get this cable that I have wound it up in this reel here, how it's twisted in there, and so this is variable. Why is it variable? It takes more work to lift long cable. If you lift the elevator half up, it takes less work to lift the cable. There's less cable, which is not as heavy as 180 feet. Right now, we have 180 feet, and each foot weighs 4.5 pounds. So that's a lot of cable. But if you're at 90 feet at 4.5, that force is a lot less. Okay? So I have a diagram here. Well, I'll have the calculus here because that's the formula we just derived a minute ago. We're going from A to B. That would be the length of the cable that has to be lifted. And force has to do with the weight of the cable. Okay? And then this dx could be a dy. It doesn't really matter. It means a very small piece of cable, because what we're talking about, as I'm lifting this cable up, we really are only lifting one tiny piece at a time. One tiny piece at a time. And as it comes up, when that tiny piece gets to the top, it's done. Then the next tiny piece is lifted up and it's going to be done. Then this is going to be lifted up. It's piece by piece by piece by piece by piece. There's the elevator at the floor, first floor, elevator somewhere, maybe in between of the top. What we say is this total distance is 180 feet from the motor to the top of the elevator. Remember where I drew the elevator touching the motor, okay? So that means as you go up, this is 180. This is 180. That's y equals 180. Once you get up to the top, it's kind of like that's your your x-axis. Then your y is equal to 0. The distance from the motor to the top of the elevator is the amount of cable I have to lift. So if the total distance is 180, 180 minus the y value that I'm at, let's pretend this is in the middle. Let's pretend this is y equals to 90 feet. Then 180 minus 90 means that distance would be now 90. If this is 90, then this is 90. So that's how much cable I have left. This is the magic function that I need, because that's the amount of cable that I'm lifting. This cable here in the middle, this slice, has to move 180 minus y, and if y was equal to 90, because this is up from 180 to 90, and they're negative numbers on the y-axis. You can think about that, but we call it positive to make it simple to use. So 180 minus this distance here, 90. Obviously, that's a 90 feet, so that function is very important. All right, what else do I have to think about? Maybe nothing. I think I already set up the integral on the next page. I did, except there's a typo. I should have fixed it for you guys. 180 minus y. So I'm going from 0 to 180. 4.5 is the weight. So now you're wondering, well, if that's my force, technically the dy is also part of it because it's 4.5 pounds per foot. So you have to multiply this by how much feet do I have? Well, how much feet do I have? It is a dy amount of feet. A dy amount of feet. It's very, 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 very small piece that I am measuring out. So that's how much. I like to put the dy in the 4.5 as the force. And then 180 minus y is always the distance to the top of the elevator. That's how much cable I have left. If I've rolled it up a little bit, that's how much I have left. If I roll it up a little more, that's how much I have left. And y keeps changing. Okay. No wonder it took me so long yesterday to get it all done because there's a lot of theory here. But it's a very simple integral. Pull out the 4.5. And by the way, looking at your guys' textbook homework, you need to do the work. You can't just rely and say, magic calculator answer. We're not experts yet. You need to practice your integration. You need to set things up. I need to see where the antiderivatives. I need to see that you plugged in the numbers and stuff like that. Some people didn't even write the integral out. Magic answers, not acceptable at all because I don't know where those magic answers come from. Okay. So I pulled up the 4.5. I'm left with a 180 minus a y dy. That gives me 4.5 times a 180y minus a y squared over 2 and 0 to 180. So I know when the 0 goes in, it's going to cancel out. So really the answer is 4.5 times 180 times 180, that's 180 squared, minus y squared, so that's going to be 180 squared over 2. And that turns into 4.5 times 180 squared minus half of 180 squared still gives me a 180 squared over 2. Because you take a whole minus half of it, you're still left with half of it. 180 squared over 2, I think, is the answer, which I'm still playing around. 4.5 times 180 times 90. There, I think that'll, because 180 times 180, divide by 2 of one of them. If you key that in, I hope that gives me the answer. And I'll let it run for a minute. Then I'll go to my calculator. You should have it done too. Did you get the answer yet? Set 7 to 900. 72,900 foot-pounds. And the only time I picked up the calculator was right here. I know time is money and money is time, but you've got to practice your brain cells. Next problem. A 5-kilogram bucket is lifted from the ground into the air by pulling on a 20-meter of rope. 20-meter rope. And they're doing a constant speed. What does that mean? This person right here, he's just pulling it like pull, pull, pull. That means constant speed implies constant force of the bucket moving up. Okay? The rope weighs only 0.08 kilograms per meter. Remember, there's 20 meters. And also remember that the more rope, when that bucket is here, that's less meters. So the force is less from the weight. When the bucket's right here, it becomes easier to get up. But when it's down here, that was hard getting that going. You know, he's pulling on it, but it was hard because of the weight of the rope. The bucket itself doesn't change, but the weight of the rope does. So I broke this problem up because he wants to know what is the total work done by the bucket and the rope. This is similar to the elevator problem, but we were only talking about the cable being lifted up to the motor, okay, to the top. We were only talking about the cable. We didn't even talk about the elevator. This is similar to the elevator problem, except that it's just a bucket of 5 kilograms that now I have to talk about. So I broke this problem up into 2 parts. Work on the bucket by itself, which will be constant. Why is it constant? Because force is equal to ma in physics. I think that came from Newton. And that means mass of something times the acceleration due to gravity, which, by the way, is, we're talking about meters, so we're talking about metric system, 9.8 meters per second squared. So that's going to go into, in 5 kilograms, that's going to go into the force of that bucket. It's just a constant force. It has to do with the weight of the bucket and the gravity on that weight. So the work done just on the bucket, work done by the bucket is 5 kilograms times 9.8 meters per second squared. Now, in reality, this is my force times d. That per second squared doesn't really matter. I care about my meter, my kilograms per meter. Okay, because that actually turns into joules, which is Newton meters. Okay, so I got to do that math. Let's see, 8 times 5 is 40. Carry the 4, 49. 490 with 1 decimal place. 49. And wait a minute. That's just the force. I didn't do the... Let me erase that answer because I'm not done. Silly me. It's part of the answer. This is the force. I still need the distance. Sorry, I was thinking that unit didn't make right for newtons, but the distance went up. Well, the bucket has to go up to 20 feet times 20 feet. Okay. Wait, it's not 20 feet, it's 20 meters. It would be ugly if I had to mix the units. Okay, now it should work out, which was 49 times 20, and that gives me, that's 18 with a 0, carry the 1, 8, 9, 980. Now I have newtons meters, which is 980 joules. All right, Moving on to the rope. Now the rope is variable, non-constant. It's variable. The more rope that's still down, the more work it's going to take. This is going to require Captain Calculus. So work on the rope will be the integral from 0 to 20, because that's how much the rope is changing. The distance from the top of him is this distance. When the bucket is here, that distance is not 180, that was the last problem. That distance is 20 minus whatever y that I am at, okay? So that's a y value from being at 0 down at the bottom, so 20 minus y. So my force is still going to be the weight of the bucket, still being acted by 9.8, and that weight is also dependent on that little slice of rope. Remember, the little slice of rope, dy, is in the calculation because when we're doing it in little pieces, we're talking about this slice of rope moving up to the top. And there's a million, zillion slices in here. We're only talking about each slice of rope, which is the thickness of your hair. So there's my dy. This is my force. This is my force. This is my force from here and here. Distance will be 20 minus y. And so I'll label that distance. Now, oh, wait a minute. My bucket was 5 kilograms. My rope's not 5 kilograms. There's a slight mistake here. Did anybody catch it before me? The rope, was only 0.08. 0.08. All right. No harm, no foul. All right. That equals to, pull out the 0.08 times 9.8, still integrating 0 to 20. 20 minus y dy, that is 0.08 times 9.8 times 20y minus y squared over 2 from 0 to 20. The 0 doesn't do anything, so my answer will be, if you can key this in, 0.08 times 9.8 times 20 times 20 is 400, minus 20 squared is 400 over 2. There's your answer. Is 0.08 times 9.8 times 400 minus 200. 0.08 times 9.8 times 200. I'll make that easy. 0.08 times 2 is 0.16, and then there's times 100. So yeah, times 100 times the 9.8. That gives me 16 times 9.8. Okay, I'll go to my calculator. What is 16 times 9.8? $156.8 joules. He wants the total, so I'm going to add my 156.8 joules plus the bucket took a lot of work, 980 joules. Whatever that is. Go ahead and think about the math on that one. Did I write it down? No, I don't have. It's big answer. I don't want to do it. Well, I'll do it. I'll do it in the calculator. 980 plus 156.8. I'll be right back. 1136.8 joules, according to my calculator. Let's see. Yep, 1113. Yep. All right. Last problem for the day, because that's as far as I got with the other class. A vertical right cylinder tank measures 30 feet high and 20 feet in diameter, and it's full of kerosene. And the kerosene weighs more than water. You know, they say that oil is thicker than water. It is. It's more dense. So it's 51.2 pounds per cubic foot. How much work does it take to pump the kerosene to the level of the top of the tank? Also, here is your tank of oil, 30 feet high, 20 feet diameter, which means 10-foot radius. And we're going to pump it to the top. Each level of oil, what I'm going to say is the bottom has a circular pool of oil. Above that is another circular pool of oil. Above that is another circular pool of oil. Matter of fact, there's a lot of circular pools of oil in this bad boy. There's a lot of them. Even the top is a circular pool of oil. But that level of oil doesn't have to go anywhere. There's just a pump right here. There's a little pump that's pulling the oil out, pumping it out. So it has to pull up think of these like paper plates. It has to pull out each paper plate one at a time. What I also need to let you know about this paper plate of oil, it may look like a paper plate of oil, but let me microscopically zoom in. It actually looks like that. That is known as a cylinder or a cylindrical disc. Each of those paper plates, even though they're very thin, every one of these paper plates is nothing more than a disc of oil. Every one of these. And that disc of oil, let me erase this excess oil here. That disc of oil that I have written here has a thickness. The height of that cylinder is a dy. So when I talk about the volume, because every cubic foot of oil weighted, was it 52.3? No, 51.2 pounds per foot cubed. So it's important to know how much oil is in this disc. The volume is pi r squared h. H is dy. R is always 10. So every disc has a volume of pi times 100 times dy. Pi r squared. 100 pi dy. That's the volume. That's how many cubic foot there is in every single. Now, dy is so small. Dy could be as small as, could be less than 0.0001. So you can see that's a very small amount of oil that every paper plate has. So this paper plate takes more work to pull it up than this paper plate. Why? The distance is more. Remember what we're always counting. This is a distance of 30 starting down here. This distance to this paper plate is a y value again. So the distance from the top to the y value will be 30 minus y. Just like the rope being pulled up. Just like the, what was the other problem? We did a rope. I already forgot what the other problem was that we had done. Oh, we did a rope. We did elevator problem. So let's set this up. Volume will be from 0 to 30. Force times distance again. My force has to do with the weight of the oil, 51.2. Okay, that's what the weight of each cubic foot. How many cubic foot do I have? I have pi. I have 10 squared. And I have a dy. Does that look familiar? Pi r squared dy, 100 pi dy, is a part of my force. But because each cubic foot, I can go back up to here and say the weight of that oil would be 51.2 times the 100 pi dy. That's the weight of that paper plate of oil. And so there's my force. This is all my force. And then I have my distance will be my 30 minus y. So, I mean, the integrations are easy on these things. It's, it's the concepts, the physics. So I pull out my constants. That's 100, that's a pi, that's 51.2. That's 51.2 times 100 pi. I can take care of that in a minute. What am I saying, volume? It was work. Hello. Work was this. 0 to 30. I'm only left with 30 minus y dy, which turns into, let me clean this up. 51.2 times 100 is 5120 pi. Integrating, that gives me the antiderivative of 30y minus y squared over 2 from 0 to 30. And again, the 0 goes away. So use your magic calculator. 5120 pi times 30 is 900 minus 900. 30 squared is over 2. That's 5120 pi times 900 minus 450. That's 5120 pi times 450. And whatever answer we get has a pi in it. So go ahead. I mean, you can, if you want to, you can just multiply these two together and put that number and call it joules. I'm sorry, it's not joules. This was English system. This is foot-pounds. Or you can multiply and approximate it. And it's a big number. I'll wait for you to tell me. Let me look at that problem. Okay, I don't have the answer in the slideshow because I got it from the textbook. Just like the homework problems you're going to have. Let's look it up. I actually had a different number in mind this morning, or yesterday, but 2A did the multiplying right. I think it's 7,238,000. And how much more oil? 229. Point, you need 3 decimals if you're going to choose to multiply in the pi. That would be 474 foot-pounds. But as I always say, you can leave the exact answer if all you did is multiply those two numbers together. All right, I didn't finish as far as I wanted to go. I wanted to do springs. I didn't get to it. And I didn't. Obviously, we're not at pressure. But I will give you a secret. The whole video of this lesson is posted in It's Learning. All right, let's look at your textbook problems. Obviously, I didn't do anything on springs. So don't do these right now. Hold off on those. Don't. Let me page. Oh, here they are. These you can do. These are your 4 homework problems. Today's Thursday, so it won't be due till next week. Okay, it won't be due till next week. I will be adding 4 to 5 my math lab. Also due Friday. Let's see, what's the date Friday going to be? Today's the 25, 26, 28, 29, 31. I don't know. It's April something. April 1st, April 2nd. All right. Okay. Thank you very much. I'm off. And, wait,